Hey guys, welcome back. I just came in from the cold shoveling, and I'm ready to warm up by doing some AP stats. Yeah. Alright. We last left off learning all the rules, okay? Normal tests. Remember, we call this, baby, the central limit theorem, and we have to have over 30 samples if we're dealing with means. Otherwise, we don't know if it's going to be normal. Doesn't matter the population. Population could be skewed out of its brain. Insane in the membrane. But if we have 30 samples, our sampling curve will be approximately normal. Alright, move on. Here we go. Let's have some fun. We got 3 math problems I want to do here today. The height of a young woman follows a normal distribution. Alright. With a mean of 64.5 inches and a standard deviation of 2.5. Find the probability that a randomly selected young woman is taller than 66 inches. Alright. So here we go. We've got our normal curve. Oh my goodness, that's bad. But, normal curve, 64.5. Now, notice what this says. How many people am I selecting? What is my sample size? Alright. Find the probability that a randomly selected woman. That means one person. What's the probability that one person? This is what Chapter 2 is all about. We only took one thing. Alright? Now, if you'll notice, now looking back, I know you might be like, this doesn't pass the normal rule, right? No, we don't know if it's going to be normal, right? Because don't we have to have 30 or more? Okay, well, hold your horses. Okay? It is stated that if it says it's a normal distribution, then our sampling curve will be a normal distribution. Doesn't matter the sample size. And if you'll notice, every single problem we've done of z-score up until now, it has had to state normal distribution. I wish I could pull up some Chapter 2 notes. But every single time, the problem should have stated this is approximately normal. Okay? And from here on out, they don't have to say that, right? As long as I have over 30 samples. Find the probability that randomly. Okay, so is 66.5. So this is a typical 66.5. This is a typical z-score problem. Something we've done from Chapter 2. And it says is taller than. So is taller than would be all of this stuff, right? So what I got, 66.5 minus what I should have got, 64.5 divided by the standard deviation. Now, if you really are feeling your kicks and giggles here, okay, you can use the formula of, remember, the formula for sampling curves is your standard deviation over the square root of n. Right? Well, our standard deviation is 2.5, right? Divided by the square root of n, which n is 1, right? Because I'm wanting to know what one girl is going to be. Now, square root of n, or square root of 1 is 1, and would you agree that 2.5 divided by 1 is still 2.5. Alright? And we never had to use this formula for Chapter 2. But now that you know it, if you really want to, you can always use this formula for standard deviation, because standard deviation is not going to change if you're only using one sample. So really, my standard deviation here is just 2.5 here. And let's see what I'm going to get for a z-score here, guys. I'm going to pause it. Alright, so I got a z-score of 0.8. Now, that doesn't mean 80%. That's a z-score of 0.8. So I'm going to use my chart here, and I'm going to look for 0.8. Right there. I'm looking for 0.80. So this right here. So there's about a 0.7881. Point P is 0.7881% chance. That's almost exact. That's kind of cool, huh? Almost exactly the same. There's a 78.81% chance that it's below 66, but it says taller than. So don't forget. Let's do this 1 minus thing. And let's see if I can do this right in my head. 2119, I think. Okay. By the way, if you want to do the inverse thing right away, if you're smart, you can just look. Instead of positive 0.8, you can look at the negative 0.8. Negative 0.8. Look at this. Woo! There she blows. And that would be the area right below. Anyways, because it's symmetric. So 0.2119 is the correct answer. Alright. Oh, 1, 2, 4. Now, find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5. Oh, so now I'm not just working with one person. I'm working with 10 girls that the average of all 10 will exceed 66.5. And ladies and gentlemen, I guarantee you it's going to be harder for 10 women to average a 66.5 than have only one average of 66.5, you know? You might be able to find one tall girl, but to find 10 of them and have it average, all right, well, let's see. Let's figure this out. So once again, I've got a normal curve centered at 64.5, all right? But this one's going to be skinnier than this, right? Because I'm dealing with 10 women. And so let's see, what would be the standard deviation for all of our samples? Well, it would be 2.5 divided by the square root of 10. So this curve is not going to be standard deviation of 2.5. It's going to be 0.5 divided by square root of 10. Bam. This standard deviation is 0.7906. Holy moly. Alright, so it's a lot smaller standard deviation than the one up here, right? And that's because it's harder to get away from the center when you have 10 women than opposed to 1. Alright, so I'm just still going to do the same thing. What I got, 66.5 minus what I should have got, 64.5, right? Divided by the standard deviation. Now remember, I'm using this standard deviation now because I'm doing a smaller curve because I had 10 women. So it's 0.7906. Alright. Okay, let's see what this will be. I'll be right back. Alright. Oh, I should have not started at that point. So, what's the probability at 66.5? Well, I got a z-score of 2.53. So having 10 women is a lot harder to reach this mark. Look at where my standard deviation or my z-score is compared to my z-score with 1. And if I look at this on my chart, I'm just going to save time, guys. I'm going to look at negative. What was that again? Negative 2.53s. Instead of subtracting from 1, I'm just going to look at negative. Man, I keep forgetting, guys. 2.53. Alright, negative 2.5. 1, 2, 3. Alright, so that is the area above. So I could go 1 minus or 0.0057. So if you guys want to, just trust me on this. Alright, so P is, and once again, I've forgotten, I have the memory of a elephant. 0.0057. 0.0057. Okay, so this is the probability of having 10 women average out to 66.5. This is the probability that only one woman can average or have a score of 66.5. A lot different with 10 women than with 1, isn't it? Right? Okay. Hopefully that makes sense. All right, let's do another story problem. This one will be our last. Based on service records from the past year, the time and hours that a technician requires to complete preventative maintenance on air conditioner follows a distribution that is strongly skewed to the right. Woo! That's skewed to the right. Most likely outcomes are close to 0. So the mean is at 1. And a standard deviation, we'll just go SD, of also 1. Alright, now that's strongly skewed though, right? So can't use my z-scores. I'm done, baby. I'm done. I'm done. Okay, that's it, guys. No, kidding. Alright. So, your company will serve a simple random sample of 70 air conditioners. You have budget of 1.1 hours per unit. Will this be enough time? Alright, so first of all, let's go over those rules. Did I do a random? Check, right? It's simple random sample, okay? By the way, this says ran. Okay? Did I pass the independency test? Indy. Alright, did I do an independency test? Do you think 70 air conditioners is less than 10% of the population? You think 70? Well, what's our population of air conditioners? People. Man, I bet you they serve over 700 people with air conditioners. I mean, for crying out loud, Janesville alone has 40,000. No, 60,000? I don't know how many people. 66,000. Alright, so I bet, assuming, alright, and I don't have time to write this all down. If I was actually doing this and I had a pen, I would write it down. I would say, yes, pass the independence test, assuming there's more than 700 people. And then, is it normal? Alright, and let's do the normal test quick. Our norm. And our normal test, or a central limit theorem, says if I sample more than 30, you know, it doesn't matter the shape of the original. If I sample more than 30, it's going to approach normal. And I'm going to go check, and I would write this down too if I had time. You know, our sampling distribution will be normal because I have over 70 people I sampled. Now, it doesn't look normal, but that's as good as I'm going to get. Alright, so it's going to be centered roughly at 1, because that's where the mean up here is, at 1. But our standard deviation is going to be slightly different. It's not going to be at 1 anymore, right? Because I'm taking 70. If I just had one of them, it could deviate by 1. But I'm taking 70. So I'm going to go 1 divided by the way, this is my standard deviation of all my samples, divided by the square root of 70. Alright, I'm going to pause it. I'm going to calculate it. Alright, so after I calculated it, it's 0.1195 is my standard deviation, meaning it's going to be pretty hard to get away from that center of 1, right? Because I might have a few air conditioning problems that are really long, but I have a lot that are at 0, right, or close to 0. So they'll kind of even each other out and kind of meet at that 1 hour point. Okay? So I'm going to do a z-score again. Alright? My z-score will be what I got. I want to know, will 1.1 be okay? Be okay, be okay. Will 1.1 be okay? What do you think? I don't know. So I'm going to say 1.1 minus what I should have got of 1 hour divided by our new standard deviation of 0.1195. Alright, what's our z-score here? I'll be right back. So, I got a z-score of 0.8733. Now remember, this is not our percentage. That's a z-score, so let's look at our z-score. 0.8, by the way, that'll round to 7. Would you guys agree? 0.87. Let's look for it. 0.87. Well, here's 0.8, so let's go to 7. Right there. So at about 8078. Alright, so what does this mean? P equals 8078. Alright, and let's put that decimal on there too. Alright, so that means basically, if I scheduled 1.1, that means I can help out all these households, right? Okay, if it was at this, you know, it's possible all of 70 households were down here. It's possible all of 70 households are here. That means 80% of the time with 70 households, this would be enough time scheduled, right? However, for about 20%, you know, 19%/20%, this is not enough time, right? 80% of the time, scheduling 1.1 hours is fine. But 20%, it would not be okay. If I'm running a business, I'm not okay with that. I would want to be sure I have more than 80%.